and welcome to everybody. I try my best to make this title as obscure as I could, but probably I was not able to discourage all of you. But before we start, I would like to ask you, is everybody in this room that knows about Web 3.0? One. Good. Transclusions? Even better. Folksonomies? Okay, so actually, it was not bad as a title. So content addressed URLs? One. Good. Blockchain. At least we ended in the right way. So the Web 3.0. So we are on the dawn on a new wave of internet application and services. And this new wave is called Web 3.0. Unfortunately, this is the wrong picture. So at some point, the Web 3.0 was supposed to be finally the semantic web. It wasn't. Actually, semantic web was supposed to be also Web 2.0, but it wasn't. So actually, when we talk about Web 3.0, we're talking about something like this. This is a very interesting picture. It's actually just a portion of the real picture. So in each column, you will find on the right the Web 3.0 equivalent of a Web 2.0 application. And there are a lot. And they are all about decentralized web, distributed systems, and blockchain. And there is a rush, like in the Golden Rush, to occupy the space of Web 3.0, delivering new amazing features or services and so on. But the hard truth is that actually we needed the Web 3.0 because of the problem of the Web 2.0 that was supposed to be about semantic web, but actually was about the social thing, the e-commerce, standards, a bit of standards as well. And we needed the Web 2.0 because of the problems of the Web 1.0. So actually, when we started this revolution a bit long time ago, we knew that we had problems. And the word was, yes, we will figure it out somehow. And to quote a very interesting article, is an interview of Jaron Lanier, which was one of the driving force behind the Web 1.0. The problem was that the original internet, the 1.0, was very bare-bone. So there was no idea of user management, there was no idea of membership, of identity, authentication, e-commerce, way to secure e-commerce. Nothing. It was very, very raw. The point was that we need to bring it out as soon as we could, because it was an exciting revolution. But in this spirit of making things fast and bare-bone, actually, that's interesting to say, the web protocol committed the primal sin of not having backlinks. So we think that the links, the linking thing, were invented by Tim Berners-Lee. Actually, it wasn't. And the way we are now used to links is actually a very specific kind of links, monodirectional links. You can go from one page to another, but to turn back, you need to ask the browser. The page you landed doesn't know about the page you were from. And the situation is getting even worse nowadays that even the European Commission started looking at the link thing and has a proposal to actually make everyone responsible of our own links. So if I put a link inside of my web page, I should be responsible if the landing page is something copyrighted or I have no right to access this page as well. So even now that we are addressing the Web 3.0, I think that we are still struggling with what I call the 5 paradoxes of digital content. So the first paradox is that content is available everywhere, but it is stored in very few places. And that's the big data silos problems that we have today. we store an incredible amount of things inside Facebook, Google, and whatever you want. So we have the illusion to being able to access things from everywhere, because it is. We can access things from our computer, our mobile phone, on the train, at home, on the move. But if something goes wrong, if the link between our device and the central station where everything is stored happen, if there is a problem, like a DDoS attack or whatever else, things disappear immediately. And think about the fact that in 2017, the 70% of the internet traffic was routed through Facebook and Google. Funny enough, even the fact that we are still struggling to move between IPv4 to IPv6 is rooted to this problem. Monopolies like netting. That's a thing that we don't think about, but that's the truth. And the second paradox is that, yes, it's easy to find something on the internet if it stays on the same place. The first time you witness the 404 error, you lose your internet virginity. So things get broken, links get broken. The average lifetime of a web page, says the Internet Archive, is around 30 days. Things move around. And that's why we invented the search engines. Because we have millions of spiders, web crawlers going around, trying to catch the pages where they are, trying to catch the movement of those pages. And thanks, that's really useful. You can now search very easily things on the internet, thanks to the search engines. But we are still struggling in properly catalog them. We are so struggling, we are so accumulating things that we need to invent machine learning to try to figure out what we have accumulated so far. So we need to process, to guess what's inside the internet. We are still struggling with content. And do you know, funny enough, what is one of the formats that was invented from the very beginning with this problem in mind was MP3. The MP3 format has this very clever idea. Let's put some metadata on the top of the file. So you can spread those files, legally or not, across the internet, but once you got the file, you got also the cataloging system. You know the author of the song, you know the singer, you know the album, you know whatever. But that was an exception. And the fourth paradox is that we're still struggling to understand the true deeply nature of digital content. Because we are still thinking in a physical way. So one of the key points of digital content is that it's easy, cheap to duplicate. And you can't tell the difference between the original and the duplicate. And that's a good thing, aside from the ones who try to enforce DRM. So we put a lot of effort in preventing access to content, and we are still struggling on the attribute things. So we can cheaply duplicate files, but we are still struggling to attribute a file to a person, the owner of the file, the creator of the file. And so we invented a very convoluted way to guess those things. Think about YouTube and how they struggle so hard to prove that the video uploaded inside YouTube does not belong to someone else. And the fifth paradox, which is the most problematic one and is the one that we haven't underestimated so far, is that for the very first time in human history, we are encoding both the media and the tools needed to read the media. So if you take a book is an encoded media. You need tools to build the book. You need to learn how to interpret the signs on the paper. But once you got it, you can read it with your own very eyes. But when you store things inside a computer, actually, you are encoding both the media, in a file, for example, but you also need tools, you need software, you need hardware to redecode it in a way that you can consume with your own senses. And this was not such a big problem. I mean, 20 years ago was not such a big problem. 30 years ago was not a problem at all, probably. If you think about yourself, 10 years ago, probably the vast majority of things that you possess, your memories or whatever, were physical things. Your assets were physical. Maybe someone of us should, at the time, could have put something inside a computer, but was just a fraction. And if you think about nowadays, probably all of us in this room have the vast majority of things inside a computer. And most of them have no physical counterpart. And we are living like if this thing will last forever. And the sad truth, it isn't. It is not. And we just start struggling with things made 30 years ago inside a computer, so with digital tapes and hard drives. And it's not that putting things in the cloud magically make this problem disappear. So the problem actually was well understood a long time ago. I don't know how many of you know about Vannevar. Vannevar was a very prominent scientist from the past century, has been the head of research and development for the US government during the Second World Wide War. So he was the top director of all the scientists working on the war effort. And was also one of the leading computer scientists in the computer analog field. And in the 30s, actually, this quote is from an article that was printed in 1945, but the idea has been developed in the 30s of the 20th century. He already have understood that at least scientists have a big information overload problem. They were not able to keep up with the vast amount of researches, discoveries that were happening all around the world. And he tried to figure out a solution. Nowadays, probably the information overload is something more common. Even my mom probably has an information overload this time with all the channels of information that she's able to listen to, television, radio, internet. Even my mom has internet nowadays. But he tried to understand how to solve this problem. And it invented a thing called the mimics in the 30s. So this is not an actual computer. This is actually an idea for an optomechanic computers. And it actually is a desktop. It's a wooden desktop. It's a table with drawers. Inside the drawers, there were the storage. And at the time, there was no hard drives. There were no hard drives. It was microfilm, the most advanced technology at the time. But it did not thought just about the storage. It was not just putting the scientists, in the hands of the scientists, information. He thought that the real problem was to also store the links between informations. He called them trails. And you see in the center of this image, there are two screens, actually. So the prototype was able to display two different books at the same time. And the very interesting thing is that you were able, through photographs, to create a link, a trail was called. And to store this trail between two pages, you could also draw on the page with a stylus, all thanks to photographic innovation at the time. And you can print and save the trail. And that was, crucial, because in Bash ideas, the knowledge is not only about storing books. This is half of the problem. Real knowledge is about storing content, but also storing the links that humans make between content. He called them trails. And the idea was supposed to print those trails and preserve those trails for further generation of scientists. So this is where the idea of the link was born. Actually, there was the Second World Wide War, then there was the digital computer of von Neumann taking the stage, and computing was, again, just about crunching numbers. There was the Cold War, there was the race to the moon. So computers were again just number crunchers. And it took about other 20 years before another visionary innovator invented what now we call the hypertext. Do you know who it is? One. Who is it? You know? Okay. It's this guy. It's Theodor Nelson. And I would like to, sorry, I hope that the audio is, we can listen to the audio? No? So, can we have the audio as well? No? No audio? Sorry? You need to select the audio. Yeah. Okay.
Hi, I'm Ted Nelson. I want to talk about the structure of computer documents. Now, most people think they know what electronic documents are because they've seen them. They've seen Microsoft Word, they've seen Adobe Acrobat. And what are computer documents like? They imitate paper. Well, when I was learning to write in my teens, it seemed to me that paper was a prison. 4 walls, right? And the ideas were constantly trying to escape. What is a parenthesis but an idea trying to escape? What is a footnote but an idea that jumped off the cliff? Because paper enforces single sequence and there's no room for digression, it imposes a particular kind of order in the very nature of the structure. When I saw the computer, I said, at last we can escape from the prison of paper. And that was what my whole hypertext idea was about in 1960 and since.
And I strongly advise you to follow this link, and find this link on the internet, because there was actually a demonstration of the project that Theodor Nelson worked since the 1960s. It was called Xanadu, was one of the biggest failures probably in the software industry. So it drew a lot of money from the 60s up to the 80s, just to being able to deliver something. It was called the biggest vaporware in the software industry. But actually, the idea inside Project Xanadu are still ahead of time today. And Theodor Nelson invented hypertext, hypermedia, and transclusions. Transclusions are an evolution of what the trails in Bash were. So transclusions in Theodor Nelson's system were bidirectional and persistent links between portion of contents and authors, making even more the associative mind of people persistent. So Bash thought that linking document was a good idea, and it is, and Nelson added authors as well. So in the 60s, he started to develop something that was called tumblers. And that's an interesting thing. So tumblers were invented in the 60s and were based not on numbers, but on numbers, which was a strange representation for fully extensible numbers. And in just this page, you can spot, we can go through a bit to this, some of the things that we invented later. So, first of all, this sequence of numbers are separated by zeros. Okay, so each portion is delimited by a 0, and each number is delimited by a point, because actually, if you look at the node, the first row, this represents a branch in a tree. So we are looking at element node 6 of a parent which is the 792nd children of the node called 2368, sorry, that was actually the children of 1. So we are seeing a tree here, flattened 1 by a tree. And the idea was that tumblers were actually transfinite numbers, so they can grow in an infinite way. And yes, the node is like a server, because in the 60s, nobody thought that it was possible that nowadays we can have a supercomputer in our hands connected to a global network. So the idea was that probably big institution could set up nodes and grant access to those nodes to people. Yes, this is similar to TCP/IP. Probably TCP/IP was influenced by some of the ideas here. But of course, TCP/IP has a limited address of numbers available, and we know this. That's why we invented IPv6. And there was no explicit, and there was an explicit idea of hierarchy also in TCP/IP, because when you look at the TCP/IP octet, it's actually a hierarchy. You are following a hierarchy, like here in the node. Then the idea of Nelson was to link a node to a user. Again, the second row is a user, which is the son of a parent, which is the son of another parent again. So it's a hierarchy. Imagine that probably companies can have employees or whatever hierarchy they want. And yes, it bounded the user to the node. Actually, nowadays, when you think about the way we are trying now to resolve the attribution problem, we are trying to give everybody a number. Okay? We are trying to give everybody a digital identity of some kind. The interesting thing about representing even user as hierarchies is that you can point in a tumbler to all the document of a specific user, just telling the user you want to. And if the user is a hierarchy, actually pointing to a root, you can point to all the children's with just one link, no matter how complex is the structure beneath. And then you have the document. And again, here there is no hashing. Of course, these are numbers. This address does not represent the content. So the other thing we talked about in the title was content addressing. We will see in a moment what it is. So this is just a number saying this is the document number 75 belonging to the user, blah, blah, blah. But then, since even the document address space is a hierarchy, you can have revisions. And this is Git for the 60s. Okay, so you can point to the same 75 document and see all its revisions. And then there is this strange thing. So you have the document fragment, which is like web fragments specification that we have now. So you know that in URI, you can specify both the document and an optional part which says, I want the charter from 1 to 10 in this document, but we are still struggling to fully implement the fragment. But the real interesting thing is that we have also a link, an address space for links belonging to a document. And that's really strange because we are not accustomed to see links separated from content. Actually, and now we are going to have a little demo, but the idea here is that the document is just about the content. It's not about the formatting. It's not about the tags. It's just content. It's an array of bytes. It's an array of bits for image. And links is something that is separated, distincted from the document. They both belong to the same object, because you see they are all belonging to 75.2, but they are in different address space. So let me just explain a bit better this thing. Sorry, just one thing more. So now we try to understand how this compares to the content addressed world that we are now witnessing in the Web 3.0. I don't know how many of you have heard about IPFS. Okay, so you know what is content addressed URL, actually. So IPFS is a tool that allows us to do very interesting thing. Just a second, okay. So IPFS is a distributed service. You can install a node in your computer. This is not a course on IPFS, trust me. The point is that when we add something to IPFS, so let's see this way. So let's imagine to have a very simple web page like this. Can you see the HTML? Okay, I can enlarge a bit more. Okay, so we can access this page from a web server, and it's very complex, and says hello world, and it has a title which says hello world. Okay, so this is a typical server addressed URL. So you have a server, in this case it's localhost, and you have the path to the document, being physical or dynamic, it doesn't matter, it's always server addressed. Actually, I can do the same thing in a slightly different way. So let's say I go to, sorry, okay. Here is where I have my web page that I show. So I can ask IPFS to add index. And what happens is that IPFS created a hash that represents the content of index.html. And with this hash, I can access the same content. So the technology behind is quite complex. You have a peer-to-peer network. This hash is not server bound, so everybody that is able to know about this hash is able to store it locally, and if more than one nodes actually has the same content, what happens when you search for this content is that you're actually retrieving blocks from each of them. So it's a very interesting technology. But let's understand what is the impact. So we may imagine that using content addressed URL solves part of the problem of the storage. So in this way, we don't have any data silos anymore. We can store things on several nodes, and no matter where they are, we can access the content. We don't care. We can host ourselves even content, so it works also in disconnected networks. And it's very, very interesting for the portion that is storing content. The hard part of this is that, yes, we can build a more complex website with links. So I have this link to another page, and I have the backlink. Okay, so if I access this page in a content addressed in a server addressed world, there is no problem. I can see my page, and I can go to the other page, and I can even go back to my original page without touching the back button. That's the good thing about server addressed things. But let's imagine that we want to store an address which is content addressed. Okay, we need to go a bit faster. So first of all, we need to know the actual content. What is it? So let's say that I want to hash talk, because I want to create a link between index and talk. Fine, so this is the hash of talk. So I can go here, and instead of saying talk, I can say HTTP. There is also a fine gateway. So I can express through an HTTP local gateway, but that's another point. So I can write this, and it works, trust me. I have just a minute, I can tell you, I can show you. But what if I want to do the same thing here? Oops, I have a problem. This is a typical chicken and egg, because in order to add the hash of the index here, I have to compute the index of the hash, but the hash, the index now contains the hash of the talk. And so I'm doomed. So content addressed is fine to store things that are not related to each other. But it's not a solution. I'm a big fan of IPFS, but it's not a solution for the linking problem. And just to give you the last piece of information before we move on, the other point, when we talk about separating the content from the links, let's try to imagine what this is a very unfair representation because it's very just for didactical purposes. But let's try to think how this document could be translated to a Xanadoc. So actually we have the real content. The real content of this HTML page is hello Codemotion, which is repeated twice, one in the title and one in the content. So in a docuverse like Xanadu, you add the content, and then of course you need the title, for example, and the H1 that we saw before. So, okay, let's say that I want to express this guy and this guy. But the point is that I can, this is just to understand, so I can express the HTML page like a series of links, of transclusions. Unfortunately, the HTML doesn't allow to transclude text. Allows you to transclude images and sounds, but not text. So if you separate the content from other things, like tags, you can have a more versatile structure. And actually, one of the key problems that we have nowadays is that we embedded, since a long ago, content with metadata. And the culprit is this guy. I don't know if someone of you can guess what it is. This is not XML, this is not HTML, this is SGML. Standard Generalized Markup Language, the grandfather of all the markups, of all the tags. Was a very clever idea for the time, so we were able to store text and semantic in the same file, but it created a mess. Tim Berners-Lee copied SGML, simplifying it, and invented the HTML, which is a mix of structure and semantic. Then we tried to, again, reinvent the wheel with XML, which is a simplification of the DTD of the SGML. But again, we are not sure about what we have invented. So its structure is semantic, what it is. And once we mix them together, it's hard to create links based on content address things. And just to talk about, you know what this is? This is Twitter. This is the largest folksonomies user base. People want to tag things. The tags of the HTML are actually the hashtags. The name is not trivial. It's the same. And again, even here, okay, we're almost done. Even here, we have embedded again the tags inside the content. And this gives us the Bermuda Triangle of content. So nowadays, we are still struggling with tagging because we intermixed tagging and content. And so, yes, we tried to build ontologies somehow, and the MP3 is an ontology. When you go inside Spotify, you are just browsing an ontology. And ontologies are made by humans usually. But we need to invent machine learning to sort out what's inside content. And people continue to add tags. Folksonomies are taxonomies built from the ground up, so by people in an informal way. And why we continue to add tags? Why Twitter is so famous about hashtags? Because tags give us the possibility to understand what we are doing. And we are human. We have been always working in the same way. We need tags that express who, what, where, and when. This is a very old story. This is the story about how we build content and we catalog content from at least 2,000 years. And mixing together those things, so mixing content and tags, actually doesn't allow us to solve the problem. And you may guess there is the last word, which is blockchain. And yes, you can store something in the blockchain. Yes, we can use the blockchain. You can use IPFS, for example, as a side storage of a blockchain, or we can use blockchain as a side storage for storing links. But please think about the future. So if you want, you can go and search for this transaction in the Bitcoin blockchain. And you need a tool, a command line tool, to understand what's actually inside. You see there is an unparsed address. Okay, if you look inside this, with the code row transaction tool from Bitcoin CLI, you will see an op return, which is actually a URL. So someone, very long time ago, stored a URL inside blockchain, which is a wise thing. Unfortunately, if you try to access this URL, it doesn't exist anymore. So, yes, content address thing is not sufficient to solve the problem. Neither blockchain is sufficient to solve the problem. We need to work together, and we need to understand how to build things for future generation. Because otherwise we are going to invent a Web3 apps that will last just a few years. And I want to finish this talk with another quote from Bash. And the point here is that we need to understand that the value of what we do is also about the association. Our mind is an associative mind. And we need to preserve those things. And we need to invent a way to finally being able to have the web as it was intended to be. Thanks. Questions? I hope many. Nobody? I don't know, I can see.
Hello.
Hi.
Thank you for your presentation. My question is really not a real question. I was just thinking if you know about this DAT project that is similar to IPFS.
Yes, I know it very well.
And I thought it would be interesting to know your opinion about that and the differences to not use blockchain as the storage.
DAT and IPFS are the two main content-addressed servers nowadays. IPFS is actually a protocol. DAT is more a service. The main difference between the two is that DAT supports fragments out of the box because it was invented and meant to be used for large data sets. So it was invented for university, sharing large data sets of data science things, and being able also to update these sets without reloading everything from scratch. So it has fragments, support, and it has another feature which actually, funny enough, makes that a sort of server-addressed things. So at some point you need to refer to a sort of naming convention that allows you not to ask every time for the new hash for the new version. Okay, so the main difference between that project and IPFS is out of the box, that actually exposes an hash that represents a node. And then you can synchronize across nodes, something that the IPFS can't. And this allows you to point always to the latest version of the content you are pointing to, no matter how many times you update this. So this is an interesting feature. Of course, I think we are still struggling to find a way to proper duplicate content. So the strategy for the DAT project is synchronization among servers. Then there is the problem of the key, because you have a private key that signs the content for not allowing people to repeat things without permission. But instead, IPFS has no such an idea. IPFS is more a raw protocol. In fact, the inventor of IPFS is building on top of it Filecoin, which is actually a more refined thing. So we are still struggling to find a way to point to the latest version of a file. The answer for that project is, okay, you have an hash that represents your latest version always, and it's always the same. And you link, actually, like in Git, you link the new version to this name. IPFS has IPNS, which is an experimental protocol that actually behaves almost like that project and is a problem at the moment because it's slow and so on. So that's why I think the idea of Nelson of having numbers can still be interesting. So we need to find a way to mix them because we are humans. We need to have reference, easy reference to files, and then we need to manage the complexity of versions and hashes and so on. But that project is absolutely one of the other technology you have to look inside. It's very interesting. Anyone else? Okay, thank you.